Today we will we will do another example. Although I mentioned in the last class that this is homework, we will do again together so that hopefully you can have more understanding on designing LED compensator. I need to go hands-on. I want you to do on the paper because this is very important. I mean, lag, after the lag, they will come out. They normally come out in the final exam because no other question in design of frequency response, lag and also lead. Okay, let's do together. I just ask you to print this one. This is the board plot. The block diagram show here, the block diagram here show a control system. It is with K equal to 6.4. The block diagram here is with K 6.4. Show that the open loop transfer function is given by GS equal to this. This one you can obtain by multiply all this in series. Okay, you remember block diagram reduction? You can multiply all this. Okay, first you solve this feedback, then multiply G1, G2, G3. You will get this. We skip this one. Hope you try. You should get this one. So the system has 4 poles, S plus 1, plus 2, plus 3. No zero. There is again 5K. For the uncompensated system, find the phase margin when system operate at 25% overshoot. That is the first question. Secondly, find the error constant, static error constant, and also steady state error when K 6.4. Okay, when overshoot 0.5%, 25%, we can use where is the graph? We can use this graph. The graph between overshoot, damping ratio, and also phase margin. We want 25%. 25% is here. 25. Okay, about 0.5. Overshoot 25%. Zeta 0.4. Okay. Zeta 0.4 here, 0.4. We can get the phase margin. Phase margin about 44. Phase margin 44 degrees. That is answering the first question. We go back to the question. Okay, here. Overshoot 20%, zeta 0.4, phase margin 44 degrees. That the first question. Number two asking us to find static error constant. Static error constant. Anyone can help. How can we obtain static error constant? How can we obtain static error constant? Anyone? From the graph. It is also asked in the test, in the recent test. How can we obtain static error constant? We can obtain the error constant by make a straight line from here, straight line, until 0. Okay, 0 here, 0 dB. The one that cross 0 dB is kV. Right, so here is about, if from my drawing here, I will redraw again. Okay, perhaps this is the one. This is kV. kV here, this is 2. Sorry, this is 0. This is 1, 2, 3. Yeah, if you use in your diagram, please make a line. Use a ruler, make a line. You may get different one. I think should be more than 3. Okay, the one that I did here, perhaps not straight. Okay, the one I obtained here is about 2.5. I will use this, but you can try. You may get different value. Okay. So static error constant 2.5 kV. 2.5. Therefore, error is 1 over kV. 1 over 2.5 is 1 over 2.5, 0.4. So 4, 2.5. 0.4 error. Okay. But if you can also, beside using the plot, you can also calculate directly using the formula. That is that will be more accurate. The one here, based on the scale, accuracy is depending on the scale. Right? So that answering the second one. Okay, now we want to design a lag compensator. Design a lag compensator to reduce the error by a factor of 20. We want to reduce by 20 while maintaining the overshoot at 25%. We want to reduce error by 20 and maintain overshoot at 20%. That means error must be 0.4 over 20. We want to reduce further. Okay? Or KV become 2.5 multiplied with 20. KV equal to 50. That is what we want. Again, this value will depend on your result, your graph. In my the one that I did before, it is larger than 2.5, about 5. But it depends. Okay, I think that is I mean the correct one should be more than 2.5. Right? This is KV 50. We want our KV increase from from 20 become from 2.5 become 50. So how to do it? We need to now find a new K. Find a new K to achieve KV equal to 50. How to do it? We will use this. The one given here. That's why the question asks us to initially obtain the open loop transfer function. So GS, KV is limit S to 0, SGS, limit S to 0, S, GS is 5K, S plus 1, 2, 3.
Doctor,
Yeah?
the overshoot value is 25, not 20.
25, okay. Sorry. Overshoot 25. But zeta correct, right?
Yes.
25. Okay, KV, if we solve that formula, is 5K over 1, 2, 3, over 6. 5K over 6. And we want it become 50. We want KV equal to 50. Therefore, K is K 560. Okay, of course 60. The 5 and 50 can be become 10, so 60. So K is 60. In order to obtain KV 50, K should be 60. Initially, K equal to 6.5 was used. Okay, remember the question here described that K initially 6.4. Okay, if K equal to 1, that will be easier. But here it was plotted with K equal to 6.4. Then now we want, if K equal to 60, we need to find how many dB that the graph or the magnitude will shift. How many it change when we use 60 instead of 6.4? How to do it? We have to multiply. We have to divide 60 over 6.4 because we used 6.4 earlier. If we use 1, then just use 60. 60 over 6.4 is 9.375. That is in normal unit, but we want in log. It's equal to 20 log log of 9.375 and 20. 19.43 dB. Okay, 20 log 9.375. So if we take a log, we get 19.43. This means that all the magnitude will be shifted up. So we increase K, will be shifted up by 19.4 dB, about 20 dB. All will be shifted. So now, what we will do, we will modify this graph. So if you print, just please all modify the graph. We want to modify by shifting the magnitude by 19 dB, 19.4 dB. We need to shift the magnitude by 19.43 dB. Okay, for example, 1 dB here, again, it will depend on your value from the beginning. If you get different K here, then the value to be shifted will be different. All right? So you please do it according to your value. So all will be shifted about 20. I will shift by 20. 20 here, one box. Here become 20. I will try to find the easiest. 20 here. Here 20. From here. Okay, so I now will draw here a new one. They're all shifted by 20. All shifted by about 20, 19.4 dB. Okay, all by 19.4. If you have a ruler that can bend that will be easier because it will be shifted in parallel to the original one. Right? So this is the new one with K60. Initially, it was K6.4. Why we use K60? Because we want to increase the KV by 20 times. Any question here before we proceed? Any question? Okay, next, we want to design the lag compensator. Designing a lag compensator. Our desired phase margin is 44 degrees. In order to achieve 25% overshoot, 25% overshoot. Usually, as I mentioned in the previous lecture, we will add a correction factor. This is not compulsory, but normally we do. We add by adding a correction factor. Therefore, the required phase margin phase margin 44 degrees overshoot. Sorry, I accidentally deleted that one. With correction factor of 10 degree. So our desired phase margin is 44 plus 10 is 54 degrees. So we want 54 degrees phase margin. If I can plot here, what that means is 0 dB here, 180 degrees. That means here we want at 0, we want phase margin here 54 degrees. That means the angle, the phase here is 180 minus 54. 126 degrees. We want 126 degrees. Okay, now let's look into the board plot. 126 degrees. One to 6 degree is here. Here 125, so about 125, about here. This is 126 degree. Okay, so that our phase margin become 54. Omega here is about this is 0 0.1, 1, 0.2, 0.3, 0.3, about 0.35. 0.1, 0.2, 0.3, 0.4, between 0.35. Here, please look into your plot. Find minus 126 degree is about 0.35 radian per second. Then we look into the magnitude at that frequency is here. Here is here. At 3.5, 0.35. At 0.35, the magnitude is 40 dB. So here, we know that it is omega 0.35. At omega 0.35 radian per second, the magnitude equal to 40 dB. We want, in order to be here as the phase margin, we want at this point, the dot plot cross 0 dB here at 0.35. How can we do it? We can do it by adding a lag compensator with the value of minus 40, because 40 minus 40 becomes 0. So we add here a lag compensator 0.8 at this point, so that when we add with the k equal to 60 magnitude and lag compensator, it becomes 0. Any question up to now? Any question? No?
No, Doctor.
Okay, so how to proceed with the lag compensator? The technique is from this frequency here 0.35, we will move 1 decade before. 1 decade before mean here 0.035. 0.035. 1 decade before that. And the one here, minus 40 dB, will be until that value, until that frequency, until 1 decade from the omega, original omega that we obtained. That is what we call the magnitude at the high frequency of the lag compensator. Then what to do? The lag compensator initially in the lower frequency will be 0. So it will be starting from 0. Must be. Why starting from 0? Because we want to maintain the kV that we calculated earlier. Otherwise, it will be changed. But if we 0, we add this one, the lag, with the original one, no change. Then kV can be maintained. Now, how can we connect? Here 0, here minus 40. How can we connect? We will connect by using, by doing a straight line with a slope of minus 20 dB per decade. 1 decade minus 20. That means this is 1 decade, 0.0 here, 1 decade. It will be minus 20, will be here. So 1 decade become different will be 20. I remove this first. So now we have to do a line, a straight line of minus 20 dB per decade like this. Please use a ruler, and until 0 dB. This is of course not accurate, not straight actually. So perhaps like this. It reached 0 at here. Okay, then that's why I initially deleted this one, because we do not know where it will cross 0 dB. So then we put 0 dB here. Erase this. This one should be a straight line. Like this. Difficult to do line here. Anyway, should be straight, minus 20 dB per decade. Right. Important point here is this point and this point. Here we know 0.035. Point here we have to read. Here 0.01, 0.001, here 0.0001, 2, 3, 4, 5, 6, 7, 8. So about this point, about 0.0008. Zero point 0.1, 0.01. Right? So now I will redraw here the one that we obtained. It is like this. One here is 0.0008 and here 0.035. 0.08, 0.035. Right. So the lag compensator is, the transfer function is first, the one going down here is the contribute to the denominator, 1 s over 0.0008 plus 1. And the one here is s over 0.035 plus 1. This is the transfer function of the lag compensator. Of course, it can be rewritten like this, 1 over 0.035 s plus 0.035 over 1 over 0.0008 s plus 0.0008. I take those out the bracket. Then again, it can be further simplified. We can simplify this part. Become 0.023. If I change this one, become all this become 0.023. So the G, the transfer function for G lag is 0.023 S plus 0.035 S plus 0.0008. That is the transfer function of the lag compensator. Any question? As I said, you have to do it to understand. Okay, once we obtain this, last question here is find the complete transfer function. Complete means we have to multiply. Now the controller is here. We have to multiply with the original system. The complete transfer function GS multiply with GCS. Okay, we have 5 K initially 5K over S plus 1, S plus 2, S plus 3, multiply with GS. GS is this, 0.023 right. This is the transfer function, the final transfer function. You can multiply times 300, 6.857. 6.857. This is the final answer. Again, I repeat, it will be not similar for all students. It will be depending on the data that you read from the graph. As I mentioned earlier, the KV that I obtained here might be different from if you do it, if you use a better, if you use a ruler, then you get different K. The one I did here is based on just estimate. Right? That answer, hope you try and design lead compensator. The correction factor 10 degree here is also an estimate. If we have if we design using MATLAB, using a computer, then we can try various value of correction factors. 10, maybe we can try 5 to get the most appropriate, to get the desired phase margin that we want. Any question before we end our lecture today? In the next class, we will move into lead compensator. We will also do a few examples and also a few past year questions regarding lead compensator.